Hello there, Mr. Sutton bringing you this lesson on volume with known cross-sections. So as the title suggests, we will be finding volume of solids that do have known cross-sections, such as squares, semicircles, all that stuff. But let's go into what we're talking about now. For our warm-up, we're going to try to visualize what's going on in one of these problems. So let's say we have the base of the solid as a region enclosed by the semicircle given here and the x-axis. So here's I'm going to just give you the straight-up graph of this thing. Your job, based off the fact that the cross-sections perpendicular to the x-axis are squares, your job is to draw this situation out, draw the solid. All right, let's see how that went for you. So we have these squares literally coming out of the page, like so, and each of these squares is perpendicular to the x-axis if you look at it in a 3D kind of way. So three-dimensionally perpendicular to the x-axis all along the length here. And you'll notice that as our semicircle gets further away from the x-axis, the squares are getting bigger and bigger. And then as we get closer to the x-axis, our squares get smaller. So if we were to flip this whole thing on its side, here's another representation of this 3D model. These are the things we're going to try to find the volume of today. So the key to unlocking the problem we just saw and all the other problems today is to realize that all these problems have an enclosed area with distance strips of that area serving as the base of some cross-section shape. So here's some more visuals. We've got squares, triangles, rectangles, semicircles. These are all possible cross-sections perpendicular to the x-axis. And the key on all of these is the base of each of these cross-section shapes, which you can eventually use to find its area. That base is just the distance strip you would be using to find the area of the enclosed region. So our general strategy for finding volume is going to be what we did with solids of revolution. We're going to find a formula for the area of a cross-section, and we're just going to integrate that over the interval of the base. So in general, our formula is just going to be volume equals integral from a to b of a of x dx, just like before. Only now we're going to have to be a little bit more creative figuring out a of x. At this point, we're going to square off against the warm-up problem. This is the same problem you had in the warm-up. We have that semicircle, cross-sections, or squares. But the good news is we don't have to draw it this time. We just have to find the volume. It's actually a lot easier. So we're going to start this by figuring out a general area formula for the cross-section, and then putting it in terms of our function x. So for squares, what's the area of a square? Oh yeah, it's a equals s squared. But now since this needs to be written as a function of x, I'm going to start by writing a of x equals s squared. And of course, I can't just leave s in there. I have to replace this with something with an x in it. So what is one side of the square going to be? The cross-section base, which is one side of our square in this case, is just going to be the distance between your bounding functions. So basically, your distance strip that you would use to figure out the area of the bounded region, you're going to use that as the base of your cross-section. So in this case, that would be top function minus bottom function, radical 25 minus x squared minus, well, 0, because it's the x-axis. So we're just going to put the square root of 25 minus x squared for that. And we could get rid of the radical, but we're just going to use the calculator anyway, so no point in doing that. Let's go ahead now and figure out the limits of integration. So for that, we're just going to find the endpoints of our enclosed region. That'll give us our integral limits. So to find the endpoints of our enclosed region, it's enclosed by this function and the x-axis. So I'm just going to set this function equal to 0. And then this takes on a value of 0 at, well, if this was 5 or negative 5, so plus or minus 5. And you could solve it more algebraically if you wanted. So now we just have to integrate this area function over this interval. So I'm going to write volume equals integral from negative 5 to 5 of, well, there's no point in rewriting all this. I'll just write a of x dx. Now it's up to the calculator. So to do this on the calculator, I'm going to start by putting my bounded functions in y equals. This will be y1, and the x-axis is just y equals 0, so I don't really need that. And then in y2, I'm going to put my area function. So that's just whatever y1 was squared. So alpha trace y1, and I'll square that. Now, yeah, I could have just written 25 minus x squared, but I'm trying to show you kind of a general process you can follow here. All right, quitting out of there, let me just take the integral of that now. So math 9 from -5 to 5, and we'll do alpha trace y2 for my area function, dx, comes out to 166.667. For this next problem, base of a solid is the region enclosed by y = 4 and x squared. Cross sections are right triangles with heights 5 times that of the leg in the xy plane. So let me just give you a 3D visual representation so you have a fighting chance on this one. So we have a horizontal line and a parabola enclosing some region, and we've got these right triangles coming out of here. The side in the xy plane is just this base of the triangle here. So given this, pause the video and see if you can figure out the volume of the solid created by this situation. Alright, so hopefully you started with the cross section's area. We've got triangles, so a of x equals 1/2 base times height is a really good place to start. But we run into a little bit of a problem here. The base of the triangle, you can see from this 3D model, is just going to be the distance between these two functions that you graphed here. However, what about the height? So when you have area formulas with more than one variable, it's a really good idea to rewrite the area formula in terms of just one variable, hopefully the base, because that's the one we know the most about. So how can we do that in this situation? Well, let me just give a two-dimensional model of our triangle. We have some base down here that we can actually express in terms of x, and then we have this height that we can't so much. So we're told that the heights were 5 times the leg in the xy plane. So this means that our height is really going to be 5 times this base down here. Plugging that back in, we have 1/2 base times 5 times base. And let's simplify this. That's going to be 5/2 b squared. So this is something we can work with a little bit more easily now. So what is the base? Specifically, it's the distance between y = 4 and y = x squared. It's just whatever you would use if you were finding the area of the bounded region. So it's going to be 4 minus x squared. So we've got 5/2 times that whole thing squared. All right, we also need limits of integration. So that's just going to be wherever 4 equals x squared. And that's going to be plus or minus 2. So let's go ahead and get the volume now. Volume is going to be the integral from -2 to 2 of the a of x that we just wrote out up here. And now it's time for the calculator. So here's what I've done on the calculator. I took my distance strip, 4 minus x squared, and I made that y1. And now I'm just going to do 5/2 times that squared for y2, and y2 is where I've actually got my area formula. Quitting out of there now, let me do my integral. So I've got Math 9, integral from -2 to 2, alpha trace y2 dx, and that comes out to 85.333. So we're going to do one more example. This time, the base of a solid is enclosed by 9 minus x squared, so upside down parabola, and essentially the x-axis. Just to make things a little different, cross sections this time are semicircles. So here's a 3D representation of this one if you like. So we have this upside down parabola. We have semicircles now coming out of the distance between the parabola and the x-axis. Pause the video and find the volume for this. All right, so for semicircles, the area in this case is going to be half a circle. So pi r squared gives us the area of a whole circle. So we can say a of x equals 1/2 pi r squared. That's our general model here. And this is where you have to be a little bit careful. Because when we were doing solids of revolution, the radius was just the distance from the axis to the function itself. But that's a different situation. In this situation here, the radius is half the base of the semicircle, half the distance between the functions. So this is the radius right here. If you just do 9 minus x squared for the base of the shape, that's great, but that's not the radius. That's the diameter of the semicircle. So for our radius, we actually need to use 9 minus x squared divided by 2. And that's going to be our area formula now, so that mixes a lot of people up. Let's find our limits of integration. That's going to be where 9 minus x squared equals 0, and that happens at 3 and -3. So our volume then is the integral from -3 to 3 of this a of x dx formula. So here's what I'm entering in my calculator this time around in my y equals. For y1, I've just got the 9 minus x squared here, the distance strip, And now I'm doing 1/2 pi times this thing over 2 squared, just like we've got going on here. Now for the integral itself, I've got integral from -3 to 3 of y2 dx, and that comes out to 101.788. So that's it for volumes with known cross-sections. Till next time, Mr. Sutton signing off.